Hi everybody, welcome back to the Data Structures and Algorithms series. In this video, we're going to be learning about linked lists. We are going to learn why we use linked lists, and then we are going to learn about singly linked lists and how to implement a singly linked list. So what are linked lists? So first, to understand what linked lists, let's talk about arrays. Arrays are useful in many applications, but they suffer from significant limitations. The size of the array must be known at the time the code is compiled, and the elements in the array are the same distance apart in memory, which can require us to have to shift when we insert a new element in the array, and this can actually be pretty expensive. So to overcome these limitations, we use linked lists. Linked lists are a collection of independent memory locations, which are called nodes, and they store data and it links to other nodes. We are able to move between the nodes by following the links, which are addresses of the nodes. And there's numerous ways to implement linked lists, but the most common way is to utilize pointers, which provide a great amount of flexibility. So now that we got an overview of what a linked list is, let's learn about a singly linked list. And after we learn about this, we are actually going to implement this in C++. So as I mentioned before, a common way to implement linked lists is to use a pointer. So a linked list is represented by a pointer to the first node of a linked list. So the first node of our linked list is called our head. In this case, A is the head of our linked list. If our linked list was empty, then the value of the head would be null. The node has at least two parts to it: the data and then the pointer or reference to the next node. So in this case, A is our data and this is our pointer to the next node, which happens to be B, which B is the data, which then our pointer points to C. C is our data. We have our pointer, which goes to D. And as you can see here, D is actually the last element in our linked list. So it doesn't have a pointer to another node, so it is null. So using this information, let's implement a singly linked list where we will insert nodes and delete nodes, and we'll also search our linked lists. So I have an empty folder here, and we're going to build our singly linked list example. I'm going to code this and explain how it works, but in the description below, I have a link to my GitHub, which includes this implemented solution. First thing we are going to do is create our node.h file. Our node has to contain at least two properties. That's the data and then the pointer to the next element. As this is a header file, we want to first define node, if and define. So this is if it's not defined, then define node. And this is a template class, so template class T. So our node is a struct node, and our public attributes are the data. So this is where our template comes in. So T data, this is just saying the type that we're going to define. If we're passing in an int, it'd be int, right? And then the pointer to our next node. So this would be node reference next. In this case, we are having node reference to itself. So this is an example of a self-referential object. Then we also need to define the constructor. We're passing nothing. We are just defining next as null. And let's make another constructor where we pass in a data and the next node. So this would be the next reference to the node. And if we didn't want to pass it in, we can make this null. And so we would be setting data equal to D and next equal to N. By making this equal null, we can actually not pass in the next reference, and that means it will default to null. You could also name this t.data, and then in this case, you would do this.data. Either way is acceptable, so just do what you are comfortable with. And then after doing all this definition, we have to do end if. So this is our node header file, and we are defining the struct for our node. It's going to have our data and then our pointer for the next node to create our singly linked list. So now let's define our singly linked list class. We'll make another header file that will be our singly linked list. We want to include node.h, and then also again do our defines. So if not defined, we're going to define, put our end if now. This again is a template class, and we define our class. So in this case, we're going to do it singly linked lists and define our public attributes. We're going to keep track of two things for our singly linked list. We're going to keep track of our head and our tail. So if you remember from the diagram, the head of our linked list is the first element in our linked list, and the tail is the last element. The tail is next pointer would always be null. So we have our node t because it's a template, and we'll call it our head, and then our node t, which is our tail. And when we initialize our singly linked list, we are going to have our head and tail be null, because when it is created, it should be an empty list. So singly linked list, head is equal to null, and tail is equal to null. We also are going to define our destructor. In this case, it's just going to be a singly linked list. We are going to learn how to insert, delete, and search for an element in our singly linked list. So let's define these methods. So the first method, insert, is not going to return anything. It is a void. Actually, all the methods that we're writing right now are not going to return anything. They will all be void methods. So it will be insert. We're inserting a specific element that will be this data, and we'll create the node actually in our method. Delete is a void delete, where we are going to retrieve a defined node that we want to delete from our list. So node, and this will be a reference to that node that we are deleting. Search, we're going to search for a specific element. So we're going to find the first element actually in our list. So this will be search t data. And finally, we are going to print out all the elements in our list. This is just so we can see that our inserts and our deletes were done correctly. So this is more of a sanity check method. So void print list. Yeah, to include the IO stream. This is so that we can outprint what the elements are in our list. We also want to include singly linked list.h. So at the top of this, I am going to leave a spot for us to write our destructor, but we'll write our destructor after we do our insert and deletes, because then the destructor is going to make more sense. Remember, a destructor is important when we are using things like pointers and references, because when we destruct, or basically spin down, this singly linked list, we don't want to have orphaned memory. So we have to go back and clean up everything that we are doing. So template class T. I'm just going to write a comment to do. And we'll go back to this. Let's start off with implementing our insert method. So template class T for our singly linked list, insert, and we take in the element data, which is of the type T. So in the case for this insert, we are going to be inserting this element at the end of our list. So this means that if we had a tail, our tail's next will now point to whatever the new node that we make. So the first thing we want to do is create a new node. So we're going to use node, that type T, and we are going to reference, so we're going to do new node T and then data. So in this case, as you can see, I'm not passing the next value. So we go back to our header file here. This was an optional value. Since I'm not passing the next, this is null, so it's not going to point to anything. So if our list was empty, we would set our head to n and our tail to n. But if our list was not empty, we would need to look at the tail and then set our tail's next to n. So how do we know if our list is empty? We would just say if tail does not equal null, then set our tail's next to n. So tail next would point to n, and our tail would be updated now to become n. Or you could say tail next. Either way, we're just pointing to that spot in memory. And that is how we know if our list isn't empty. Remember what I just said earlier, if our list is empty, then we set our head equal to n and our tail equal to n. So this is how we insert an element to the end of our list. If you look at this insert logic and you remember from our previous videos when we talked about time complexity, what do you think that this complexity would be? If we look at it, we say if the tail is not null, then we set the next value, and this is a constant time. Otherwise, we set the head and the tail to n, which is another constant time. So in this case, 1 plus 1, if we're saying this is O1 and this is O1, makes this overall time to be done in O1. This is constant time. And I made a little mistake here. I just forgot to say the return type is void. Now, let's do our delete. So in our delete, in this case, we want to delete a specific node. So this would be node T, and this is I'm going to call it the node to delete. Let's add a little bit of logic here. If our list is empty, we should just stop. So we want to have a fail-safe of not just going through here. So I'm going to say if our head is null, which means that then the list is empty, we're just going to stop. So in this case, I'm just going to write out an error, print f list is empty. Otherwise, we can continue looking for this node. So we go else, we need to find the node. So there's a couple of scenarios that we need to consider. The node to delete could be the only element in the list. So in this case, there's only one element in the list. So in this case, we would say if our head is equal to our tail, in this case, that means there's only one element in the list, and our head is equal to the node to delete, then we will deallocate the memory of our head. So we're going to delete our head and then set our head equal to null and our tail equal to null. Another scenario that we have to handle is that if our head is actually the node that we are going to be deleting, but there is not only one element in the list, there's more than one element in the list. So that means if we delete the node, we have to make the next element of the node to delete become the new head. So else if the head is equal to node to delete, our head has to equal our head's next item. Otherwise, the scenario is pretty much the same. We have to iterate through the list and find the node to delete and then update its predecessor's next value to the node to delete's next value. So look back at the diagram that we had. If C was the element that we needed to delete, then we would iterate from A, go to B, to C. We'd be paying attention to our previous value, and we have to change B's pointer to now point to D, because that's what C points to, right? So B's pointer would change to what C is referencing to. Else, node T, this is how we're going to keep track of our predecessor. And this is going to start at the head of our list. And then we are going to walk through each element of our list and find the node before the tail. So while predecessor's next does not equal the node to delete, our predecessor is going to equal to our predecessor's next element. We're going to stop when predecessor's next is node to delete. So then we break out of the loop. We change our predecessor's next to our node to delete's next. So this is going back to the example here where we're going to change B's next to C's next because we are deleting C. Then last but not least, we need to deallocate our memory. In this case, we are going to deallocate the node to delete. So we're going to write delete node to delete. So now that we've written our insert and delete, I think we probably have a good idea now how we would want to write our destructor. So let's go back to our destructor method and deallocate the memory. Basically saying that while our list isn't empty, we are going to delete each element in the list. In this case, we can just keep updating our head until there are no more elements. So first we'll set a node, and this will be just the element that when we're iterating through the list, we'll call this P. It's our placeholder. And we say while head does not equal null, we're going to set our P equal to our head, delete the head, which is deallocating the memory, and then setting our head equal to our placeholder. So here we're just going through our list and deallocating memory if the list is not empty. So now we have written our insert and our delete. Let's write our search method. Well, in this case, we have template class T, which is going to be a void singularly linked list, searching for our data. So in this case, what we're going to do is we're going to just print out the index that we found the data at. So if it's not in the list at all, we're going to just print out -1. Otherwise, we're just going to print out what element number it is in the list. So what we're going to do is something similar to deallocating our memory. We're going to say we're going to have a placeholder. So this could be our node T, where our P is actually equal to our head. So we're going to create a placeholder, and this placeholder is going to be equal to our head, and then we're going to make a counter. So int counter, that's going to equal 0. And while P does not equal null, if P's data is equal to the data that we're looking for, then we're going to break out of our while loop. Otherwise, we need to iterate our counter. So we'll just do counter plus plus. We also need to then set P equal to P next. At the end of this, the goal is to print out where the element is in the list. So we would write printf, and we're printing out our counter. Now, there's one scenario that actually we didn't handle when I said that the element doesn't exist in the list. So in this case, the element wouldn't exist in the list if P happens to be null. So if we actually wrote if P is equal to null, we are going to print -1. Otherwise, we print the counter. There's lots of ways to write this. This is just a really quick first pass. Look at these things and see how you can optimize the code. So now that we've looked at our search and also going back to delete, can you see what the complexity of these are? Well, let's look at our delete first. In our delete, if there's only one element in our list, that is constant time. Otherwise, if the node to delete is our head, that is also constant time. But if the node to delete is inside the list, then we have to iterate through each element in that list, which means that this is O n time, which goes back to our search. We have to iterate through each element in our list in order to find our data. So again, this is O n time. All right, there is one more method that I said we were going to implement, and that is our print method. This is a void for our singly linked lists. And we are going to print the list. And this just goes through every single element in the list and just prints it out. So this could be similar to our search. We will have a node T, which is our placeholder, equal to our head. And while P does not equal null, and I'm just going to do a C out here. So std C out P's data, and then a space. We will make then P equal to P next. And then finally just do an end line so we can just see everything printed out on one line. So that is all the elements I said we would implement. Let's now test this code. So I'm gonna make a new file here. And this is gonna be called test.cpp. This is just testing all the classes and everything that we've written to implement our singly linked list. Let's include our IO stream. Let's include our singly linked list header file. Going to be using namespace std, and let's define our main method. So int main. Let's make a new singly linked list. So we're just going to do a singly linked list of the type int. We'll call this list. In this case, now the list is empty. So how do we know that a list is empty? Our head is null. So we can write cout list.head is equal to null. And in this case, this list will be null, and therefore this will print out 1. So before we just compile this code, 1, we need to make file, but 2, we are also working with template classes. We have to declare to the compiler that one of the classes is an int. So I'm just going to add template class singly linked list int, and this is happening down on our main file, and then I'm also going to add this to the bottom of this. I'm going to quickly add a makefile. You can view this in the GitHub repo. If you want to learn how to make a makefile, that is another video for another time. Right now, I'm just going to add the makefile very quickly. So now after adding the makefile and declaring our templates, let's build our code. So I built the code, and then I'm going to run the main exe that got created. You can see here it outprinted 1 because our list is empty. Let's add a node to our list. So we're going to call list.insert, and let's insert 1. After doing this, our list.head should outprint 0, right? So let's do this again. Save, run our make, build, and it outprints 0 because it is not empty anymore. The head is populated by 1. Let's insert another element to our list. So let's insert 2, and let's print out our list. So we're going to call list.printlist. As you can see, that our list has 1 and 2 in it. Let's insert one more element to our list. Let's insert 3. If we print the list, it would be 1, 2, 3. And what we want to do is actually delete our middle element. So we're going to delete 2. That would be the heads next. So we're going to call list.delete, and we're going to do list.heads next, and that is the node that we are going to delete. If we've successfully deleted this middle element, we should now get an outprint of 1 and 3 as the only elements in our list. So let's check. There you go. You've learned how to implement a singly linked list, and you have some working examples. You can take this even further. You can write an insert statement that inserts at the beginning of the list, or it inserts after the nth number in the list. And you can also write methods that specifically just delete the head, or delete the tail, or delete the nth element in your list. Take what you've learned here and expand on it and write other methods that kind of tease your brain and make you think about other ways to use this singly linked list. In our next video, we're going to learn about doubly linked lists and how to implement them, building on this singly linked list example. All right, until then, happy learning.